All right, 7.3, sampling distribution for proportions. This is where you're finally going to get to use that p-hat that I was talking about with the samples and parameters in 7.1. P-hat is the sample for proportion, which would be p. It's like this. Let's say I've got a population of maybe free throws that Steph Curry shoots. His population's shooting percentage for free throws might be 90%. But I go out and I collect a sample of 10 free throws. I figure out how many he makes. He makes 7 of those 10, so his p-hat would be 0.7. Okay, and you can use that to make some sort of inference on whether or not the probability of him shooting that is blah. I just run through. N is the fixed number of binomial trials. R is the number of successes. P, it's not the probability we're talking about. P is the probability of success for each trial, and we'll use Q as the probability of failure. Make sure you double check that NP is bigger than 5 and NQ is bigger than 5. Now it doesn't matter if N is 30 or bigger. With the central limit theorem, it doesn't really apply. It's the binomial approximation for the norm or under or using the normal curve that we have to use instead. So those two things have to make sure they work in order to use the normal curve. The mu will be the population probability, and standard deviation is going to be a little bit different. It's going to be the probability of success times failure divided by the sample size, and then take the square root of that. Okay, so your standard error for p-hat is simply the standard deviation of p-hat, and we're going to have to make some sort of discrete continuous correction just like we did before. Okay? If you remember before, we had all these rectangles that were in a histogram that had, like R is 0 success, 1 success, 2 success, 3 success, but we had to convert to some sort of X value by taking halfway in between those two bars. Okay, well, on the X-axis is R. On your Y-axis is the probability of Y, I guess you say R over N, or basically probability. But now on the x-axis, what we're doing is we are going to R. We're going to really find the probability that this probability is going to happen. If that makes any sense? So instead of it being rectangles and you've got 0, it's going to be 0 over how many trials. So 0 over 10, 1 over 10 over 0.1. 0.2. So now our correction has to be 0.5 over n. Okay, and n is how big of the sampling size it is. Now that might got too theoretical for you. I'm sorry if it did, but hopefully the next couple of examples will help out with that. And again, feel free to ask as many questions in class as you possibly want. So here we go. Suppose that the annual crime rate in Denver is 0.111, or basically 1/9, 1 out of 9. If 50 people live in this apartment complex, what's the probability that between 10% and 20% of residents will fall victim of a crime this year? All right, so first we got to check to see if we can actually use the normal distribution. So here's your n of 50 people. Your probability of success, that's 5.55, which is bigger than 5. That's good. Okay, just barely, but it works. And then 50 minus 0.889, okay, that's 44.45. That's bigger than 5. Okay, that works. So therefore, we can use p-hat as an approximation for this distribution. So what we're really trying to find is what's the probability that p-hat is between 10% and 20%. Now, don't forget to convert those into decimals. Okay, our probability of getting robbed, or success is getting robbed, I guess, is 0.11. The standard deviation to go along with that, so PQ divided by the 50, because there's 50 residents in Denver that we're interested in. Okay, and then we're going to use the standard deviation of 0.044. Our continuous correction isn't going to be adding or subtracting 0.5. It's going to be 0.5 divided by 50, again, because there's 50 people in Denver. So we're going to have to add or subtract 0.01. So now when I think of my rectangles, I think of a rectangle that's got in the middle of it a point 10, and another rectangle that has in the middle of it 0.2. Well, I want that edge and that edge. Okay. In fact, I think I need to make a correction here because I gotta ask if it's going in between or between. Okay. So I really don't want that edge. My bad. I want that guy and I want that guy. So 0.1 plus the correction and 0.2 minus the correction. And I got those two values mixed up on the notes then too. Okay, and that's all because I want to find the area in between. So now that I've converted those into x values, okay, that's going to change a little bit. And that's going to change a little bit. I'm going to use p in the standard deviation to find out z-scores. So 0.11 minus 0.111 divided by 0.044. Okay, this is going to change a little bit to negative 0.02. And then 0.19 minus 0.111. Let's see, minus 0.111. Okay, divided by 0.044. Okay, that's going to be 1.7. Actually, it's going to be 1.8 when I round. Yeah. I'll find the areas between those two. 1.8 is going to give me an area of 0.9641. Negative 0.02 is 0.4920. Okay, so that's going to leave us with, let's see here, about 4721. Okay, so there's about a 47% chance that between 10% and 20% of the residents will be a victim of a crime next year. So a percent of a percent. Yeah. Again, we can practice those in the rectangles and how to add and subtract that continuous error more in class. You have control charts that go with these proportions. It's used to examine an attribute or quality of an observation rather than a measurement. We select a fixed number of size n at fixed number of time intervals and determine the sample proportions at each interval. We then use the normal approximation for the sample proportions to determine the control limits. So basically this is all saying we're going to use your standard deviation and your p in a way, that idea of 2 standard deviations and 3 standard deviations way to get your control limits. P bar, this is the first time this will show up. It's the total number of observed successes in all the samples. So if I've got 10 different samples, I'm going to add up all the successes. I'm going to add up all the trials, and that's going to be your P bar. Be careful with that. That's going to be your center line. You're going to use P bar to find Q bar divided by how big each sample was to figure out 2 standard deviations away and 3 standard deviations away. Your out of control signals are just like they were for the sample one. If you got one data that's 3 standard deviations away, it's out of control. Signal number 2, 9 consecutive that are above or below the middle is out of control. And the third signal, if there's 2 of the 3 that are 2 standard deviations away, then that's out of control as well. Okay, so what I pulled from is a problem in the book. Trying to think of what page it's on, but it's a proportion of A's in a certain class. Okay, here's your P hat. Okay, in the middle of 0.1750. Okay, 2 standard deviations above, 2 standard deviations away, below, 3 above, and 3 below to get those blue kind of boundary lines. And then you just kind of make your data points, connect them, And now C, because of this 1 here is 3 standard deviations away, you would say that this set of data is out of control. Again, we can practice this more in class. Okay, here's your assignment. On page 387, try 1 through 9 odds. Do as many as you need to, and we can answer a lot more questions and practice this when we get to class.